Friends, welcome to my channel. Today we discuss the properties of determinants and some of their applications. Here is the first property. The value of the determinant remains unchanged if its rows and columns are interchanged. You can see in the diagram the rows have been made into columns, then also the values of the determinants remain same. You can see it's been highlighted there. The first row, the elements of the first row, namely A11, A12, A13, have become the elements of the first column in the right hand side. Similarly, the second and third row have become the second and third column. But then also the two values will remain same. You remember one thing? In case of a square matrix A, in case of any matrix actually, if the rows and columns are interchanged, then it is called the transpose of the matrix. By this property we can say that the determinant of a square matrix A is equal to the determinant of its transpose, that is determinant of A equals to determinant of A dash. So this property can be used for a transpose of a matrix. Here's the next property, property 2. If any two rows or columns of a determinant are interchanged, then sign of the determinant changes. Here you can see I am giving an example. Here we have done what? We have interchanged the first row with the second row. You can see the highlighted part. First row has been made into second row and second one as the first row. Then we have put a minus sign in front. Okay, so that means every time you change any two rows or maybe any two columns, then the sign will change. Number 3, property number 3. If any two rows or columns of a determinant are identical, means all corresponding elements are same, then value of the determinant becomes 0. We can see an example here. In this first example we have seen that R1 is equal to R3. The elements of the first row and third row are same. And in one more example you can see the elements of the first column and second column are same, therefore both the values of these two determinants become 0. Here comes the next property, number 4. If each element of a row or a column of a determinant is multiplied by a constant k, suppose k, then its value gets multiplied by that constant k. To show that, we can assume that there be a 3 by 3 determinant denoted by lambda. Let us multiply the first elements of the first row by k. You can see in the highlighted part. Then that k can be taken common from the determinant. It can be taken out of the first row. And what is the value of the determinant? We have assumed it to be lambda, therefore it will become k times of lambda. That means if we multiply any row or any column by a constant, then the whole value of the determinant gets multiplied by that constant. We'll do some examples later. Now see the next property. If some or all elements of a row or column of a determinant are expressed as sum of two or more terms, then the determinant can be expressed as sum of two or more determinants. We can give you an example here. Consider the determinant containing the elements like 2, 6, 8, 6, 3, 1 and 2, 2, 2. Now you can see the elements of the first row R1 can be splitted in that way. 2 plus 0, 0 can be written, no problem. 2 plus 4, 2 plus 6. Now we can split it into two different determinants having the elements, other elements same. So in that case, the value of the determinant becomes the value of the second determinant only, because in the first determinant, you can see in the first determinant the first row and the third row are identical, therefore its value becomes 0. That's the way we can use the property of, in this particular property, in calculations. Here comes the next one. If to each element of any row or column of a determinant, the equimultiples of corresponding elements of other row or other column are added, then value of determinant remains the same. You can see an example here. That means if suppose the ith row, Ri means the ith row, the elements of the ith row are added to the k times of the elements of the z row, or you can say the elements of the ith column are added to the k times of the elements of the z column, then the value of the determinant will remain same. We can give you an example here. Again, let lambda is equal to this 3 by 3 determinant. What we have done here, we have done the operation R1. We write the operation side by like this. R1 goes R1 plus k times of R2. That will mean that we have added the elements of R1 with that of k times of the elements of the second row. We can write it here like this. You can see the description below what we have done. So we have to write the operation nearby like that in the bracket. Okay, there is one more property of determinants of triangular matrix. First of all, what is a triangular matrix? See, a square matrix is said to be triangular if the elements of one side of the diagonal equal to 0. You know the diagonal elements. I can show you by example. You can see this is a square matrix whose diagonal elements are 2, 3 and 2. 2, 3, 2. And below the diagonal we have zeros, all zeros written in red in color. And this is a triangular matrix. It is called an upper triangular matrix. One more type of triangular matrix is this. Here we have got 2, 7 and 8 as the diagonal elements, and above them the red zeros are there. This is called a lower triangular matrix. What is the property related to determinants is here. The determinant of a triangular matrix equals to the product of the diagonal elements. Yes, you can see. We can consider that particular example. 2, 3 and 2 are the diagonal elements. This determinant is of an upper triangular matrix. Its value will be nothing but 2 into 3 into 2, that is nothing but 12. Okay, we can have a lower triangular matrix in this way. 2, 7, 8 are the diagonal elements, and therefore its value. Let me use the properties of determinant in proving some examples from your book. First, consider this one. You have to show that the value of this determinant equals to 0, but without expanding it, only using the properties. Here you can see the solution. What we have done here, we have added the elements of the first column with the elements of the third column. What operation we have done should be written side by like this. Okay, the value of this determinant becomes 0. Again we have used the property here. what property we have used is C1 and C3 are identical. That is the property 3. You can see the elements of the first column and the third column are same, therefore its value becomes 0. This is quite easy. Again, come to this one. The solution is you got to operate R1 equals to R1 plus R2 plus R3. This means we add the elements of the first row with the elements of the second and third row. Then the first row will change. You can see what will it become. Then all the elements of R1 becomes equal to 0. You can see it will cancel each other and all the elements of the first row will become 0. And if all the elements of a row or a column becomes 0, then the value of the determinant always becomes 0. That's how it can be proved very easily. Okay, come to this problem. Here we consider the left hand side and do what? We add the elements of the third column with the elements of the second column to get the elements of the third column like this. You can see we have written C3 means third column, and only the third column has changed. The first and second columns are remaining same. Whatever column or row is changed should be written side by. So what other elements now have become? AB plus AC plus BC, that is the first element of the third column, and similarly second and third elements of the third column. Actually all are same. Again, because the three elements are same, actually that element can be taken out of the determinant like this. We just take a common. We write it thereby taking out AB plus BC plus CA from C3. Then only 1 will remain there. Again, you can see in the determinant the first column and third column looks same, means they are identical, hence its value must be equal to 0. The property is there, so the answer is equal to 0. Proceed to the next problem. Here you have to consider the left hand side of the problem like this, and you have to eventually get the answer in the right hand side. So what we do, we do the operation like this. R1 means first row, the elements of the first rows will be changed. What will you get? R1 goes R1 minus R2 minus R3, means the elements of R2 and R3 are subtracted from the elements of the first row, and you will get it like this: minus twice A minus twice B minus twice X, and the second and third row will remain same. In this step we take out 2 from R1 from the first row, and then you can see the next operation is R2 goes R2 minus R1, means the second row changes. We subtract the elements of the first row from the second row to get C, R and Z. Similarly, R3 goes to R3 minus R1, that means the elements of R3 become B, Q and Y, but it is not there in the right hand side. The right hand side should be like this only. How do we make it? We interchange the third row and second row, and you remember, while interchanging two rows, the sign of the determinant changes. That's how it becomes the right hand side. Okay, I have written there and below. See the next problem. Here you have to prove the determinant equals to the three factors, product of the three factors like this. The solution will be in this way. Take the left hand side of the equation, and what we do, we subtract the elements of first row from the second and the elements of the first row from the third to get like this. So our target is to make it a triangular matrix, in fact an upper triangular matrix. You see, we can take out the common parts. That means B minus A can be taken from the second row and C minus A can be taken out from the third row by factorizing the elements. Now we can see one more operation we do right now. It is R3, means third row minus the second row. If you would subtract the elements of the second row from the third row, you will get it like this. And what you get it here is an upper triangular matrix whose determinant will be equal to the product of the diagonal elements. Already we have discussed it in the properties. So the values will become like this. So already it is written there, you can see it. Now by reordering the factors we can get the answer as desired. This is an example of a similar kind. So try to solve this particular example by yourself. Here you have to apply the column operations. See the next problem. Here consider the left hand side, and can you see what operation we have made it here? We have added the elements of the first column with the elements of the second and third column to get twice of all these, twice. A 2 will appear there, and since all the three elements of the first column are same, therefore you can take it out of the determinant like this. There will be 1 1 1 in the first column, and again as earlier we can make it into an upper triangular matrix by this operation. You can see the second row minus first row, and the third row minus the first row. Again you can see the elements in that way, and it has become an upper triangular matrix. Since it is an upper triangular matrix, by properties of determinant, the value of the determinant is equal to the product of the diagonal elements, which are written in red in color. Now you can see it is nothing but the cube of the same factor. It will become the right hand side. Okay, that's all for